Good morning all of you. In today's session we deal with the wave equations through a circular waveguide. Okay, wave equations through a circular waveguide. Now in the previous class we have dealt with the wave equations through a rectangular waveguide. Now we will deal with the wave equations through a circular waveguide. So after we complete this wave equations through circular waveguide, we deal with the cavity resonator being constructed by using a circular waveguide. Okay, so therefore let us first of all look into this basic equations, how we normally going to derive. So already we know the basic Maxwell's equations. Del cross E is equal to minus j omega mu h. How do we got this del cross E is equal to minus j omega mu h? Del cross E is equal to minus dou b by dou t. Okay, so minus dou b by dou t, b is equal to mu h. So therefore I will be getting here as dou mu will be coming out dou h by dou t. So if h is going to be taken as the time varying component, we can replace h is equal to h naught into e power j omega t, right? So if you differentiate that with respect to time, you are normally going to get this particular equation. So normally we are going to start with this equation. Similarly, similar to the rectangular waveguide, here also we are going to solve with this. We are going to start with this particular basic equation. Okay, so this is what the starting point for the expression to solve. Exactly same procedure we are normally going to implement. That means what are all the steps we have to do here? Well, the first step is we have to start with the Maxwell's equations, and we should solve these Maxwell's equations, right? And we should try to get the expressions for what is that components in terms of get the exponents in terms of the various components for the cylindrical coordinate system. Now when you think about a cylindrical coordinate system, what is that you are going to have? You are normally going to have a cylinder like this. That means if you consider a cylinder, right, so if you simply going to chop the cylinder perpendicular to the surface of the cylinder, you will be getting the circles. So that is how we normally written this here as circle. Now one of the side of the two sides of the cylinder are going to be circles for us. So therefore I can represent this as a circle now. Okay, this is a circle now. So now if this is a cylindrical coordinate system, imagine now it is going to have three axes: x axis, y axis, z axis. Now we are converting this Cartesian coordinate system into a cylindrical coordinate system. Now imagine it is a z axis. Now the wave is propagating along the z axis. If the wave is propagating along z axis, imagine this is x axis, say this is y axis. Now this is the vector of our concern. So now if you take a point, if you take any point on the surface, this point what I can write as equal to rho, phi and z. These three are the points on the cylindrical coordinate system. So now for a circular waveguide, we consider a cylindrical coordinate system. That means we imagine that the cylinder is normally placed in a, we normally assume that the circular waveguide is normally placed in a cylindrical coordinate system. So the circular waveguide is placed in a cylindrical coordinate system. So now we normally apply the conditions for the cylindrical coordinate system in order to get the expressions, in order to get the wave equations for the circular waveguide. Okay, so let us have this circular waveguide now, because the cross section of the cylinder is normally going to be only circle for us. Okay, now this angle phi is nothing but azimuth angle, which is normally going to make an angle with the vector under consideration with respect to x axis. It is known as the azimuth angle for us. So rho is nothing but the radius of this particular circular plate. So this is circle if you consider. So for this circle we normally going to have a radius rho, and z is always now here we normally going to have y here, because y is another axis, wave is propagating along z axis. So we can take here as y or z. So it is up to us to consider, right? Here I am considering as z. Now we will be having 3 points, okay, rho, phi and z points. So as per the cylindrical coordinate system. So here you can take as something like y here. Okay, so these are the points we can have it here. Now what is most important here is we have to solve these Maxwell's equations. So once we solve the Maxwell's equations, then we apply the conditions for TE mode and as well as for TM mode. So we already know for TE mode, transverse electric mode, EZ components are going to be 0, and for TM mode, HZ components are going to be equal to 0. So based on whether you are looking into TE mode or TM mode, we normally going to solve the generalized equations whatever we get from this particular solution from the Maxwell's equations. So first of all, we solve the Maxwell's equations and we get the differential equation in terms of the various field components, and after we get the field components, then you have to solve for the electric field or magnetic field along the z direction. If you are talking about TM mode, in TM mode HZ is 0, so you should solve for EZ. In TE mode, you should solve for HZ equation. So once you get HZ equation, then by applying boundary conditions, we normally going to get the HZ or EZ equations. So after we get the HZ and EZ equations, we substitute them in the equations that we get from after solving the Maxwell's equations. Okay. So after solving Maxwell's equations, we get some equations. So we kept them aside. After we kept them aside, now based on the mode of communication, whether it is TE or TM mode, we find out either EZ or HZ equations. Then these equations we have to substitute in the equations that we got after we solving the Maxwell's equations. So to get the overall wave equations, these three are the basic steps we normally going to have, right? So first step is going to be you have to solve the Maxwell's equations. Second step is going to be what now? By applying some boundary conditions, we are going to get the equations for either HZ or EZ components. Then after that, we have to substitute those equations in the equations that we got by solving the Maxwell's equations, right, to get the overall wave equations. So these three are the various steps we have to solve. The same steps we have used already while solving the wave equations for rectangular waveguide. So therefore, let us start working with this particular thing now. So first equation we have is del cross H is equal to minus j omega mu H. Now this we are dealing here with a cylindrical coordinate system. So therefore, in cylindrical coordinate system we can write the determinant for this particular curl operation going to be equal to what now? A rho a phi, because this arc distance is always going to be rho a phi. Arc distance is always going to be rho a phi. Okay, for a particular, that means if you wanted to know the amount of flux radiated in this particular direction, so compulsory to know rho a phi. So therefore we are going to have rho a phi and Az, right? Az is going to be another component which you are going to have. Now we will solve this particular equation now by putting now similar to the previous one. In the previous one, what is that you are going to have now? You are going to have in the cylindrical coordinate system, you are going to have x, y, z as the coordinates. In the cylindrical coordinate system, in the Cartesian coordinate system, we have got x, y, z coordinates. In the cylindrical coordinate system, you are going to have rho phi z coordinates. Okay. So now here I am just solving it very conventionally, therefore I will be considering it as z here, right? So let's don't bother about y or z there, right? So we don't bother about this z parameter here, we bother about only these two to solve the equations for us. Okay. Now for this what we can have now? Next one is, I can write like this, the next for the electric field components, because I am writing this equation on the LHS we have electric field. So I will be putting here for electric field components. So these electric field components what I can have now? E rho E phi and Ez. Rho E phi and Ez components. Okay. Rho Ez components. Right. So that means according to the coordinate system I will be writing here as z and this is going to be y. Then this particular point what I am representing on the coordinate system is will be normally holding good for us. So now with respect to this we are writing this particular equation. Now whole into 1 by rho we will write. That means 1 by rho into this determinant matrix is equal to what we are going to have now. That means the entire curl operation is normally going to be done with respect to rho, because rho is normally going to be the constant over this particular circle. So therefore for the entire determinant we calculate by 1 by rho. is equal to minus j omega mu h. Now this, how I can write this h as, h can be done in terms of a rho, a phi and a z components. So a rho component is going to be h rho, this is going to be h phi and this is going to be h z components. So like this we expand this particular equation. Now after we expand this equation, what we will do now? We have to find out the determinant value for h rho and a phi components, sorry h phi components. So for this, first of all, I wanted to go with the h rho component. So for this, what I will do now? Simply this 1 by rho into h rho means what? I will close this particular section. Now I simply find out the determinant value for this. So dou Ez by dou phi minus rho dou E phi by dou Z I will get is equal to which component I will be looking for? I will be looking for a rho component. So what is a rho component? Is going to be minus j omega mu h rho. So I name this equation as 1. Similarly, I will go with the second a phi directed electric field component, magnetic field components. Now what I can have here? Just close this one now. Now what is that? I am going to write 1 by rho minus a phi minus rho a phi L, right? So therefore a phi, anyway a phi component is the one which I am looking for. So therefore I just skip this a phi. So I will be having minus rho of what I will be having Ez by, sorry, dou Z by dou rho minus dou E rho by dou Z I will get, okay, is equal to minus j omega mu h phi. Now I can name this as equation number 2. Similar to the above equation, I will solve for del cross H. What is the equation for del cross H? Del cross H is equal to j omega epsilon E. I can write. Now let us solve this. Now while solving this equation, this determinant is going to be same. Determinant is going to be same. Means what? The left hand side of this equation is always going to be same. Only thing is E is replaced with H. That's all. Therefore, by seeing this equation, I can write this particular equation. How? 1 by rho of into dou hz by dou phi minus rho dou h phi by dou z I will write is equal to, what is there I have on the right hand side of this equation? J omega epsilon E rho component. Similarly, I will go with the second one now. In the second one, what I am going to have, this rho simply will get cancelled. And next one is, in this equation, this is minus, here I have minus, this minus will get cancelled, I will get plus over there. But whereas here, what I will be having now in the second component now, this is the first component. What about second component I have? This is the second component I will be having. So this second component is minus of, anyway this rho will get cancelled, minus of dou hz by dou rho minus dou h rho by dou z is equal to j omega epsilon E phi. So these two are the equations. Now I can name this as equation 1a, I can name this as equation 2a, right? Now in these equations, if you see carefully, we have dou E phi by dou z. Now the wave is propagating along the z direction. Now therefore we have to solve for this component, for the differential component with respect to z coordinate, right? Similarly, I can go, this E5 and H rho are normally orthogonal to each other. So these two components we have to compulsorily consider, which are E5 H rho, and next one is E rho H phi. These two are the orthogonal components for us. So that means from these two equations I can solve to get the equations in terms of H rho, H phi, E rho and E phi components. That is what very important for us. So therefore now we know we can write this equation E phi. Here I have E phi to solve. So therefore E phi is equal to E phi naught into e power minus j beta z. Why it is going to be minus j beta z? Because the wave is propagating along the positive z direction. We will take this as e power minus j beta z. Right. So once you differentiate this equation once, then we get now minus j beta of E phi. Same component I will be getting here. So we will put this value in equation 1. I have this equation 1. Let us substitute this in equation 1. What I will be having now? 1 by rho dou Ez by dou phi minus rho of What is this equation? Dou E phi by dou z, just now I got here minus j beta into E phi. Okay, is equal to right hand side as it is, minus j omega mu h rho. This minus into minus plus, then 1 by rho into dou E z by dou phi plus j beta rho E phi I will be getting, and the right hand side I will be having minus j omega mu h rho. So I can name this as equation number 3. Similar to the above, I can just take it from the equation 2. I can solve for equation 2 for h rho. So that means here h rho, E phi all are going to be same. So this h rho, what I can write this h rho as? H rho is equal to h rho naught into e power minus j beta z. Same thing I will write. Whatever that I have written here, same thing I am writing for the magnetic field along the rho direction. Right. So once I differentiate this equation once, I will be getting minus j beta into h rho component as it is. Right. Is equal to, on the right hand side, what is that I have? J omega epsilon E phi. So I will be solving this equation 2 for dou h rho by dou z based on this particular basic equation. Now once you substitute in this equation, what I will be having, this minus of this minus j beta part will be coming over here. So therefore I will be having minus into minus plus, this factor I will be getting. Alright. Now from equation 3, now where is equation 3? I have named this equation as number 3. This is equation 3. This is equation 3. From equation 3, I can get the value for h rho. So h rho is equal to minus 1 by j omega mu sigma of all this part. So similarly I write this particular part over here, all that part I will be putting over there. Then after that we normally going to substitute. Already in this equation, what is that I have now? I have E phi. See this? I have E phi component. See this? I have E phi component. So this, instead of E phi, I will get E phi from equation 4. E phi is equal to minus 1 by this particular part on the RHS, I will be taking on to the LHS. So 1 by I will be getting 1 by minus 1 by j omega epsilon of this particular component, dou hz by dou rho plus j beta h rho. So this component I will be getting. So this E phi I will substitute in this particular equation. So in this equation, once if I substitute this, what is that I will be having? Minus 1 by j omega mu rho of dou Ez by dou phi plus j beta rho, okay, j beta rho into h rho. So that means into E phi. What is E phi I have? This is E phi. Now I am substituting this E phi, entire E phi, whatever I am getting from here, I am substituting here. Now I have to solve for the h rho component. Similarly, once if I get h rho component, I have to solve for the other components like E phi, okay, and other rest of the components. Now what is that we have got? H rho is equal to, we have got this equation, minus 1 by j omega, minus 1 by j omega, minus 1 by j omega mu sigma dou Ez by dou phi plus all this component we have got. Now we'll try to solve this equation now. First of all, we'll solve the innermost bracket. Innermost bracket means we expand this with minus 1 by j omega epsilon dou Ez by dou rho. This is minus into plus minus 1 by j omega epsilon j beta h rho I will write. Then after that I will expand with the outer brackets. Okay, so now I will write dou Ez by dou phi minus into plus minus dou beta rho by j omega sigma. So j omega epsilon dou hz by dou rho minus, what I will have now, minus into plus minus j beta rho by j beta epsilon into j beta by h rho. So this is what equation I get. Now in this, if you see carefully, this jj can be cancelled, here also jj can be cancelled. Alright. So here if you see carefully, you are going to get the components beta rho by omega epsilon, which is common. So therefore I will take them as common outside. So once if I take them as outside common, then I can write this equation as dou hz by dou rho plus minus of beta rho by omega epsilon has been taken as common. So this is be obviously plus j beta h rho. Then next we will solve for the outer brackets. So this 1 by minus 1 by j omega mu rho into dou Ez by dou phi, I'll write. This is minus into minus plus. Now I'll just simply expand. So beta rho by omega epsilon into this component. Okay, 1 by j omega mu sigma. This minus into minus has become plus. So you should solve this carefully. Mistakenly if you put minus here, then you won't get the solution. Right. So now into this component I'll write dou Hz by dou rho plus this minus into minus already plus. So therefore b rho by omega epsilon into 1 by j omega mu sigma into j beta h rho. Now if you see this carefully, we can cancel out these rho components, we can cancel out this jj components. Right. Now we have to solve this equation to get into the final h rho expression. So the equation what we have got now, h rho is equal to all this equation we have got. Now in this equation if you see carefully, this first part is remained as it is, 1 by minus 1 by j omega mu sigma dou Ez by dou mu rho dou Ez by dou phi as it is, I'll write. The next component is what now, this beta by j omega, j, now this omega into omega is omega square. Okay, so that means j omega square mu epsilon I'll write into dou Hz by dou rho plus beta square, this beta into beta is beta square, then omega square mu epsilon, omega square mu epsilon into h rho. So I will be writing the same components. Now for simplification purpose, I let k square is equal to omega square mu epsilon. Now I will just simply substitute wherever I have this omega square mu epsilon with k square. So I will be writing like this. Now once I write like this, then I have h rho here, I have h rho here. So therefore I will take this h rho which is there on the RHS into the LHS. So therefore this h rho into what I can write this as 1 minus beta square by k square I can write. Alright, so is equal to right hand side remains as it is, minus 1 by j omega mu rho dou Ez by dou phi, okay, plus beta by j k square dou Hz by dou rho. That is the equation I have. Now this, by solving this equation, h rho of, I can write this as k square minus beta square by k square, I'll be writing here, is equal to right hand side as it is, j omega mu sigma dou Ez by dou phi plus beta by k square into j, okay, dou Hz by dou rho. Right. Now we have to solve for this equation again, right. So we will take this k square minus b square by k square onto the right hand side and we will solve for it. Now we will be solving this equation. This equation, what we do now, this part k square minus beta square by k square, I will take it onto the right hand side. Now once if I take it on the right hand side, what will happen now? It will become like k square by k square minus beta square, and this part remains as it is, minus 1 by j omega mu sigma into dou Ez by dou phi plus beta by j k square into this part is k square by k square minus beta square into dou Hz by dou rho. Now what I can do is, now these two got cancelled, k square I have here, k square I have here, they get cancelled. Now what is actually k square means? K square is nothing but equal to, we have substituted here, k square is equal to omega square mu epsilon. Now that k square I can substitute here, this k square I can substitute here is equal to omega square mu epsilon. Now here mu get cancelled, omega one time it will go, and the rest of the components remains are going to be what now? I will be having minus 1 by j by this rho will be as it is. Then from here I will be having omega epsilon, that will be coming over here, and next I will make another substitution, that is k square minus beta square is made equal to some constant kc square. For simplification purpose, I will simply make that is equal to some constant kc square. So therefore what is that I will be having now here? So minus 1 by j omega mu sigma k square by k square is what this. So this kc square already I have substituted, no, right? So we made as k square here, or otherwise this part I can have here as 1 by kc square. So this part I have replaced as kc square. K square anyway has come over here now. So into dou Ez by dou phi. The next is beta by j kc square into dou Ez by dou rho. Now to solve this equation we have to take the common kind of a components. To get into common components, what I will do is on either side I multiply and divided by j component. I multiply and divided by j. So here also I multiply and divided by j. When I multiply it and divided by j, what will happen now? This becomes j into j square. J square means what? Minus 1. So this minus into minus becomes plus. So therefore what I can still substitute this as equal to now? I can write this as equal to h rho is equal to minus, not minus, plus 1 by, this j has vanished just now. Okay, so this 1 into omega epsilon omega epsilon, let us write it 1 by, that is omega epsilon by rho into j by kc, into j by kc I will be having, okay, into j by kc square, okay, plus this component, this other component that I will be having, which is going to be plus. Now here I want something like j by kc square, since j by kc square is coming over here. So therefore this j into j becomes j square, is going to be minus. So therefore I will be writing here as minus beta into dou hz by dou rho. Okay, so this j into j has vanished as minus 1, j square as minus 1, beta into all that particular part, into j is there here, minus into minus has vanished. So I will be having here j by k square, so into j by k square. So this is the equation that I will be writing here. So now let us take out the common components. Now j by k square is common now, so into dou Ez by dou phi, that is there, component is also there for us. So let us write that part into dou Ez by dou phi minus beta j by k square dou hz by dou rho. So that is the equation that I will be writing here. Now once I write this equation, then I have to take the common, I have to take out the common components. So the equation what I will be getting here as h rho is equal to as j into j is j square, which is equal to minus 1. So minus into minus becomes plus. So I will be having here omega epsilon by rho into j by k square into dou Ez by dou phi minus this j into j is j square, which is minus 1. So minus beta j by k square into dou Ez by dou rho. Now if you see this here, j by k square is really, kc square is common. So j by kc square is common. So I can write this h rho is equal to, I will take common j by kc square, I will take common. So once if I take that as common, I will be having now omega epsilon by rho dou Ez by dou phi minus, I have beta there, beta dou hz by dou rho. So that is the equation that I will be getting for h rho. So like this I have to get all the equations for E rho, H rho, E rho, okay, H phi and E phi components, right? So by solving in a similar methods, we will be getting the other components as well. Now by solving in the similar grounds, we will be getting the expressions for H rho. So already we have got the expression for H rho. Okay. So sorry, this is what already we defined now. So here this equation is 5. We can name this equation as 6. So we got H rho. H rho has something like this, j by k square into all this factor. Similarly, we can solve it for E rho, E phi and H phi. Okay. So E rho I can take as equation number 6. This is say equation number 7 and this is say equation number 8. Now 5, 6, 7, 8 equations are the governing equations that you are going to have. Now in this equation, if you are looking for TE mode, if you are looking for TE mode wave equations, what will happen now? Ez in TE mode, Ez is equal to 0 and Hz is not equal to 0. That is the condition we have for TE mode. For TE mode, Ez is equal to 0, Hz is not equal to 0 because it is transverse electric field along z direction would be 0. So therefore in TE mode this Ez component becomes equal to 0. That means wherever you have Ez here, so all these Ez components simply becomes equal to 0. We left over with only Hz component. Means what? You have to get the expression for Hz value by applying the boundary conditions. Now similarly, if you are looking for TM mode, in TM mode Hz is equal to 0. I'm sorry, this is Hz is equal to 0. Transverse magnetic field, no? TM mode. Transverse magnetic means the magnetic field along z direction would be equal to 0 and Ez would be not equal to 0. In TM mode, wherever you have Hz component, okay, you have Hz component here like this. So dou Hz by dou phi simply becomes this factor becomes equal to 0 and you have to find out the expression for Ez value by using the boundary conditions. Okay, so now in the next class what we do is we will try to solve the expressions for Ez and Hz by applying the boundary conditions, and here we are going to use the Bessel functions. Already in mathematics by this time you might have studied about the Bessel functions. Now we use the Bessel functions. That means here mathematics, we are going to use mathematics as a tool. The final equations, final solution of the solution of the complex equations we solve by using the Bessel functions. Okay, so straight away we are going to represent in a Bessel functions and we apply the boundary conditions to find the appropriate field components. Thank you very much for today's session.